so let us talk about Lewis structures. And in this section, we're going to refer to Lewis structures for molecules. Previously, we talked about the Lewis symbols for atoms, such as, let me make this bigger here, such as in the case of oxygen. Remember, we said that the Lewis symbol for oxygen would be simply the symbol for oxygen, which is O, followed by the number of valence electrons, which in the case of oxygen will be 6, and therefore this would represent the Lewis symbol for oxygen. Or in the case of chlorine, it would be this, where the dots represent the valence electrons, all right? So that's basically how we draw the Lewis symbols for individual atoms. But now we're going to look at how we do the same thing for molecules. Let me get this working here. Okay, so that's what we'll be looking at. Now, in order for us to do that, we have to talk about the covalent bond, right? And this is basically a force of attraction that occurs between atoms as a result of sharing electrons, right? So within molecules, you're going to find that the atoms are linked to each other by pairs of electrons, and they're held together so that the atom or the molecule can exist as a discrete unit. So a covalent bond consists of a pair of electrons being shared between two atoms. And I should say here that the two atoms would have to be non-metallic atoms. So let me just put here, let me see if I can squeeze it in here. Non-metals, non-metallic atoms. All right? Okay, so that's what we mean by a covalent bond. And most of the compounds that exist in nature, or exist at all, contain predominantly covalent bonds, all right? So, as a result of the covalent bond that exists between atoms, then basically the resulting collection of atoms can exist as a discrete unit known as a molecule. So, an example of this would be carbon dioxide. And what you're looking at here are some models representing carbon dioxide, where the gray sphere represents carbon and the red spheres represents oxygen, and as you can see, they exist as discrete units, right? Where you have one carbon atom bonded to two oxygen atoms, all right? So basically, in covalent bonding, we have sharing of electrons between molecules or between atoms in a molecule. Now, what we're going to look at here are some examples of diatomic molecules such as hydrogen, chlorine, iodine, and nitrogen. And in each of these cases, we have electrons being shared between the two atoms. In this case, and in this case, we have two electrons being shared between each atom, right? And therefore, we have a pair of electrons being shared. Now, in the case of nitrogen, this is a bit different from the others, because in the case of nitrogen, we have three pairs of electrons being shared between the two nitrogen atoms, all right? Now, this is one way of representing it. So these are actually Lewis structures, but there's another way that is a bit more convenient, where we use a line or a dash to replace the pair of electrons being shared between the two atoms. So for example, in the case of the hydrogen molecule here, it can also be represented this way, where we have H, a dash, and then H, and it's understood that the dash here is the same thing as a pair of electrons. And we can do something similar in the case of the chlorine, in the case of the iodine, right? Now, in the case of the nitrogen, we have three pairs of electrons being shared between the two nitrogen atoms. So therefore, we use three dashes or three lines to represent the three pairs, each line again representing a pair of electrons. Another thing I want to point out here before we move on is that in the case of chlorine, iodine, and nitrogen, and this is true for most of the covalent compounds that we're going to meet at this level, the electron sharing takes place such that each atom ends up with 8 electrons on its outer shell. And that's important because basically that 8 electron arrangement confers a great deal of stability to the structure, all right? We call that the octet rule, right? The octet rule basically says that when you have sharing of electrons, the atoms tend to have 8 electrons on its outer shell. Now, that is not always true, and actually we won't get into any examples of the exceptions, but for our purposes, we're just going to stick to those situations where there are 8 electrons on the outer shell. So as we can see here in the case of chlorine, nitrogen, and iodine, all the atoms involved have 8 electrons. Now, hydrogen is a bit unique because hydrogen cannot have more than 2 electrons on its outer shell, right? So hydrogen satisfies what we call a duet rule, right? Only 2 electrons can be shared between the 2 hydrogen atoms. Okay, so that's what happens in these simple molecules. Now, we're going to look at some more complex structures, not too complex, but, more complex than the ones that we have just looked at. So what we're going to look at is how do we draw the Lewis structures for these particular molecules. And as stated here, when you're drawing the Lewis structures, the most important consideration for forming a stable compound is that the atoms obtain the noble gas configuration. And the noble gas configuration is the octet rule that I was referring to. In other words, each atom must have 8 electrons on its outer shell. So let me just write here that here you should have 8 electrons in the valence shell. Let me put valence shell. It's the same thing. All right? Okay, so that's basically what we try to do. The most difficult part of determining the Lewis structure is determining basically how the atoms are arranged. In other words, which atom would be in the middle and which atoms will be surrounding the middle atom, right? In the case of simple molecules with more than 2 atoms, one atom will be the central atom surrounded by the other atoms. So, for example, in the case of this molecule here, there are 2 possible arrangements. You could have 2 chlorines bonded to each other, and then 1 chlorine is bonded to an oxygen atom, as seen here. Or you could have the oxygen atom in the middle bonded to 2 chlorine atoms. So the question now becomes, which one would be the correct one? And usually, not in all cases, but usually, the atom that is single and or the atom that is less electronegative atom will be the central atom. Now, what do we mean by the less electronegative? We may encounter this term later on, but just to suffice to say, the atom which is to the left, let me write this down here, the atom which is to the left and below will be in the center or in the middle. All right, and I'm talking about with reference to the periodic table, right? So, for example, well, this would not be a good example because in this case, oxygen is a single atom here. But I'm thinking something along the lines of, let's say, you have carbon dioxide, right? Well, not only is the fact that carbon is a single atom here, but if you look at the periodic table, in period 2, you'll see that carbon is to the left of oxygen. So therefore, as a result, carbon would be in the middle, and then it's surrounded by the 2 oxygen atoms, all right? So that's usually the most difficult part in determining the Lewis structure, figuring out which atom is in the middle and which atoms are surrounding. And as stated here, it is usually the single atom or the one that's less electronegative, which means the atom which is to the left and below of the other atom in the periodic table, all right? Okay, so let's go through the procedures for the drawing of a Lewis structure. Key thing you need to remember or determine is the number of valence electrons, which can be easily determined by the periodic table, the position of the element in the periodic table, and more specifically, what group that element is in. So, for example, chlorine is in group 7A, so it has 7 valence electrons. Hydrogen, which is in group 1A, has 1 electron, and so on and so forth, right? So that is basically how you're going to tell the number of valence electrons that are present in the atom, and that will help you to determine the Lewis structure, as you're going to see in a couple of examples here. So the first step in determining the Lewis structure is that you determine the total number of valence electrons. So you go to the periodic table, you look up the group numbers of the elements involved, and you add them up, right? And that gives you the total number of valence electrons, right? We're going to skip this for the time being. I won't go into that. This deals with ions, and we have not discussed ions yet. So let me skip this here. And then we talked about this example here, water, right? So in the case of water, you have 2 hydrogen atoms and 1 oxygen atom, right? So basically what you'd have to do is go to the go to the periodic table and look up the group numbers, right? And you'll see that in the case of hydrogen, there's 1 electron, 1 valence electron provided. but there are two hydrogen atoms. I'm sorry, there are two hydrogen atoms. So the total number of valence electrons from the hydrogens will be 2. And then in the case of oxygen, which belongs to group 6, so therefore the total number of valence electrons will be 6 plus 2, and therefore you're going to end up with 8 valence electrons. So that's the first step. You determine the number of valence electrons by simply going to the periodic table and look up the group numbers, which gives you the valence electron numbers, and then you add them up. The next step is that you write a skeletal arrangement of the atoms and connect them with a single covalent bond. Now remember, each line represents a pair of electrons, so you can use a dash or you can use 2 dots, it doesn't matter. In the case of hydrogen, however, whenever there's a hydrogen atom present, it can only form 1 covalent bond, all right? Very important for you to recognize that. So in the case of oxygen, it can have a maximum of 2 covalent bonds, all right? So here is what the arrangement would be in the case of the water molecule. So basically, you're going to have the arrangement like this, and then you're going to put the dots or lines to represent the bonds between the hydrogen and the oxygen atoms. So this is what it may look like, or it may look like this. Or, let me draw the other possibilities using the lines or the dashes. Or you can say O bonded to H, bonded to 8, right? So far we have used 2 of the 8 pairs, or I should say 4 pairs of electrons, right? Because it's a total of 8 electrons that you'll be using. So basically, the number of valence electrons that are remaining after you have used up 2 pairs would be 2 more pairs, 4 electrons, right? So the question now becomes, where do those 4 electrons end up? And the answer is that those 4 electrons will end up on the oxygen atom. And it's going to look like this right here, or this right here, or it's going to look like this. H, O, H, and that would be the Lewis structure for the water molecule. All right? So that's just a simple example, and I can go through a couple more examples. In fact, I think what I'll do in class is go through some more examples so that you get a feel for how we determine the Lewis structures of the molecule, of any molecule that you're given. Before I leave this, I want to say here that what this gives us, the information that this gives us about the water molecule, is how the atoms are connected and where the bonding pairs and the lone pairs of electrons, which are these pairs here. Basically, that's all it gives you. It does not say anything about the shape of the molecule, which is important and which we may discuss later on. All right? So let me do another example here. So let's say you're asked to draw the Lewis structure of carbon dioxide. All right? So we go to the periodic table. You see that carbon belongs in group 4. So therefore, it will contribute 4 valence electrons. And oxygen belongs to group 6. But because there are 2 of them, we have to multiply that by that 6 by 2. And that gives you 12 electrons contributed by the 2 oxygen atoms. So therefore, the total number of valence electrons here would be 4 plus 12, 16 electrons, which is equal to 8 pairs of electrons. I like to work with pairs. Then I put the carbon in the middle, surround it with the oxygens, and then I would use 2 of the pairs, 2 of the 8 pairs, to form 2 bonds here and here. So that leaves 6 pairs. So the question is, where will those 6 pairs go? And the answer is that they will end up on the oxygens like this and this. All right? Now, one would not stop here as a final answer. And the reason why is because of something we said before about the octet rule, right? Remember we said that these structures will try to get an arrangement where each atom ends up with 8 electrons on its outer shell. Now, this oxygen here has 8 electrons. You have 2, 4, 6, and then this pair here. The same is true for this oxygen. However, in the case of carbon, carbon only has 2 pairs, right? Or 4 electrons on its outer shell. The carbon needs to have 8, and the best way that happens is that this pair of electrons come here to form a bond. This pair of electrons come here to form another bond, and therefore the final structure for carbon dioxide will be this. And now every atom in this structure has 8 electrons on its outer shell, right? The oxygen has 8 electrons, which is 2, 4, 6, 8. This oxygen has the same arrangement, and the carbon in the middle has 2, 4, 6, 8 electrons, all right? And therefore, this here would be the final answer as far as the structure, the Lewis structure of carbon dioxide is concerned. Okay, I'm going to stop here. Let me just skip all this here because I just covered all of this here. And let me just check something here just to see if there's anything else. Okay, so I'm going to stop here for today, and then I'll post another video concerning another topic. In fact, the other video will go into chapter 4. All right? Until next time.